was close. I'm still a young man. All right. Everybody, on the AP test, all right, and also my final, there's a lot of questions with average in it. You know, the average value of a function, average rate of change, find the C that satisfies a mean value theorem, which kind of thinks of average, and then find the instantaneous rate of change at a value. I'm using the same function, a trig function, through all, well, I guess it's 5 problems here, all right? And it's really important we understand the language of each. All right, so I'm going to work these out. If you want to pause, or if you guys want to try to work ahead of me. These would definitely be no calculator. These would definitely be. Yeah, I'll give you guys a second. These would definitely be no calculator. I'd probably tell you to show the derivative. I might let you do it with calculator, but I would say show the derivative. So you still have to take the derivative. And that way, if you forgot your rad, you wouldn't get it wrong. I'm less likely to punish you for not understanding rad on the final than the AP test is. You bet. Write that here. So I think in this case, because you went 0 to the power 2, it should be power 2 minus 0 on both sides, right? You're going to have the sign mistakes off. All right. All right, I'm going to give a push on the first one. All right, if you're going, just ignore me. All right, now you don't need a graph, but again, I like making graphs because it gives us a good feel for what's going on. And hopefully you remember your cosine function looks something, whoops, a little better than that. Looks something like this between the two, okay? Here's what I want you to realize. This is definitely a positive area under the curve. And F, we're asking for the average value of the function. So I'm going to replace the green area under the curve with the black rectangle. And they're going to, the green area and the black area would be the same. And the F average is the height of the rectangle, right? Or the Y value. That's the average of the function. We know to integrate the area under the curve, pi over 2 of cosine x, right? And that's going to be equal to the length of the rectangle, which is pi over 2 minus 0, and then the height, F average. All right? When I do this problem, the integral of, and then again, derivative of sine is cosine, so that works. And I'm going to integrate it from pi over 2 to 0. That's pi over 2 times F average. Sine of pi over 2, and again, if you're not sure, you can practice this, but it's 1 minus 0. So sine of pi over 2 is 1, and sine of 0 is 0. So I get 1 equals pi over 2 F guys, for number one, f average is 2 over pi for height. Okay, and that makes sense to me, guys, because if I picture this in my head, I have kind of a, for rough shapes, I kind of see a triangle that's 1 high and 1.5 long, you know, and that's roughly 0.75 for area. And then I have this rectangle, 2 over 3 is like 2/3 times the same. I can see how that would be approximately the same. You know what I mean? I can picture it in my head. So the area works out. All right? On number 2, okay? Again, this was the average value of the function, all right? This is the average value. The next one says find the average rate of change. All right, and the average rate of change, and again, you don't need a graph, but I'm going to probably use the same graph over and over and over here. I'll tell you what, I'm going to make a good picture of it and not do it again. The average rate of change is, you know, what's happening from the first point to the second point. And in this case, guys, our average rate of change is just that. It's just a secant line, right, between these points. So really, it's just as fast as you can write it. And if I can go f of pi over 2 minus f of 0 over pi over 2 minus 0, cosine of pi over 2 minus cosine of 0 over pi over 2. And everybody, we should immediately recognize this should be negative, right? Because this is downhill in the graph. Right here. This is a negative slope. And what I get here is 0 minus 1 over pi over 2. Now this is kind of a fun one because this time the rate of change looks strangely familiar, doesn't it, to the average value, but it's the opposite sign. So the rate of change of this function is negative 2 over pi when we finish it. All right? That's coincidental. The truth is, when I set the functions up on the board, I didn't think about how the answers would look. I just wanted to pick a trig function. All right? So there we go. We've done the average value of the function. Now we've done the average rate of change of the function. Let's move over to the other page. We'll go single page here. Yep. Okay, I'll pause. So then I want you to do the mean value theorem and find the instantaneous rate of change of the same function. So everybody, this C value is going to go 4 decimal places for number 3. It is not a clean question. Mean value theorem states that the instantaneous rate of change, or the derivative, equals the average rate of change between 2 points. We just figured out on the last problem, right, the average rate of change? We all agree that we found that slope was negative 2 over pi. If you go back a little bit in the video, or go back to the previous page, we could show that f of b minus f of a over b minus a was negative 2 over pi. What we're saying is there's some point C, if I do this in a different color, where the yellow and the blue have the same exact slope. And I want to know that C value. And in this case, there might be more than 1 point, but I'm pretty sure this time there's just 1. You can tell from even our little crappy graph. So on the right side here, hopefully you guys realize the derivative of cosine x is negative sine x, right? So over here you get negative sine c. 2 negatives make a positive, so I get sine c is equal to 2 over pi. So I'm going to have to do inverse sine in rad of 2 over pi. So again, a lot of times students don't like this calculation, but it's not that bad. You're in radians, sine negative 1, 2 over, and I'm going to use the exact pi, second, and get pi in there, right, because that's what it is. If I hit enter, it comes out to be 0.69. I'll try to, ooh, that's not a good place. 6901 is what I see. All right, 0.6901. So my C value here is 4 decimal places. All right. And does that make sense based on our interval? Absolutely, right? Pi over 2 is approximately 1.5-ish, right? So 0.69 falls right in the middle. Okay? Last one. and it's got two parts. Find the instantaneous rate of change at x equals pi over 2 of cosine x. All right, now f of x equals cosine x. Well, instantaneous rate of change is just the, you just got to take the derivative, and we found it in the previous problem. It's just negative sine x. All right, and if I work my way down the page, and then you just got to evaluate it at that function value, right? So it becomes f prime of pi over 2 equals negative sine pi over 2. So I think the instantaneous rate of change, sine of pi over 2, sine of 90 is 1. So this is just negative 1. All right, that's the instantaneous rate of change. We're done with 4. It is just a number. If and often, especially on the AP, they want you to find the equation of the tangent line. Well, that takes two things, a point and a slope. You have the slope. You know that f prime of pi over 2 is negative 1. Question is, you don't have a y value, right? I just gave you the x, and it's so important we understand that we're not plugging in the derivative here. We're actually plugging into the original function to find the y value, right? We want a point on the curve. And I think we find that f pi over 2 is equal to 0 this time. Cosine of 90 is 0. Again, these are unit circle problems, good practice for us. So I would do this point slope form. Y minus 0, right, equals negative 1 is the slope, x minus pi over 2. On the AP, if it says solve for y, we really want to make sure we take the time to do at least to do this step. And if there's a value here, just send it back into the other side so y is alone. All right? These are some of the most confusing, if I go back to dual page to show them. These are some of the things that students most often confuse with each other when we're working on problems. All right? Keep on practicing.